Professor Mitchell. Today we're starting chapter 7, which is about estimating parameters and determining sample sizes. We're going to start in section 7. To make an inference about the value of the corresponding population proportion. So my favorite example for this is whenever there's an election coming up, there are always a lot of polls. And so they'll call, 1,000 people or something, and they'll say, do you plan to vote for candidate A or B? And let's say 52% of those sampled say they're going to vote for candidate A. Then your estimate for the total proportion of people that are going to vote for that candidate would be 52%, but there would be some margin of error attached to it because you're only asking a sample, okay? So concepts related to that are the point estimate. So in the example I was just describing, that would be the 52%, the 0.52. That would be your sample proportion, which we're going to call p hat. That's the best estimate I have for the population proportion. Once you get that sample proportion, you make it into a confidence interval. Use the sample proportion to construct a confidence interval estimate of the true value of the population proportion. So if you ever listen to news reports and they say, in this sample, 52% said they were going to vote for candidate A, and the margin of error is plus or minus 3%. What that means is that we're pretty confident that the true proportion of people who are going to vote for that candidate is within 3 percentage points of 52%. So between 49% and 55%. Okay. And then if you want your margin of error to be a certain size, let's say 3% was too big and you wanted to bring it down to 2%, we can figure out how large a sample do I need to get that margin of error. All right, so let's start with point estimates. Point estimate is a single value used to estimate a population parameter. So remember, in this section, we're talking about proportion. That's the parameter. So the sample proportion, p hat, is the best point estimate of the population proportion p. This we don't really need to spend a lot of time on, just talking about biased versus unbiased estimator. This is basically saying that if you look at the sampling distribution, remember, back in section 6.4, we talked about sampling distribution of the mean. P hat, or population proportion, also has a sampling distribution. And we say that p hat is an unbiased estimator because its distribution has the same mean as the distribution of the population parameter. All right, so here's an example. A Gallup poll was taken in which 1,487 adults were surveyed, and 43% of them said that they had a Facebook page. Based on that result, find the best point estimate of the proportion of all adults who have a Facebook page. Well, this is a pretty simple example. Your point estimate would just be your sample proportion. It would be 0.43. Okay, that is the best point estimate of P. Remember, P is the population parameter. This value would be called p hat because it's coming from the sample. All right, now we talk about confidence intervals. So a confidence interval or interval estimate is a range or an interval of values used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated CI. So this is when you attach that margin of error to your point estimate. Now, each confidence interval comes with what's called a confidence level. So this is a probability That probability is denoted 1 minus alpha. This is the Greek letter alpha. So 0.95 is a commonly used confidence level. The probability that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. That confidence level is also called the degree of confidence or the confidence coefficient. So these are the three most common confidence levels that we're going to be using. Occasionally you do see a different one. We're going to talk about what this means exactly. It's kind of easy to describe this incorrectly, so we're going to be careful about that. I'm going to be careful about that when I talk about it. Notice that if the confidence level is 0.90, that means the is 0.99. That means alpha is 0.01. Okay, so interpretation of a confidence interval. We have to be careful to interpret them correctly. The correct interpretation, say that your confidence interval is P is between 0.405 and 0.455. It would be correct to say we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion P. That would be a correct thing to say. It would not be correct to say there is a 95% chance that the true value of P will fall between those two values. Value of P or it doesn't. It's not appropriate to attach a probability to it. It also wouldn't be correct to say that 95% of sample proportions will fall between 0.405 and 0.455. Okay. That depends on a number of factors. The size of the sample is one of them. Okay, so let's just go back to this is how you will usually hear me say it when I have to interpret it. We're 95% confident that that interval contains the true value of P. Think of it this way: if you took 100 different samples, it would be okay to say that probably about 95 of them contain the true value of P. Okay, and that's exactly what's illustrated in this picture. So we have 20 different confidence intervals. So these correspond to 20 different samples. Each sample is going to have its own value of P hat. And so when you construct that confidence interval, the vast majority of them are going to contain the true value of P. So in this picture, the true value of P is 0.5. Notice there is one interval that does not contain P, right? So I believe there are 20 samples here, 19 of them contain the true value of P. All right, that brings us to critical values. A critical value is the number on the borderline separating sample statistics that are significantly high or significantly low. So we've talked about this a number of times. In this picture, let's see, we're trying to find a value of Z such that that value of Z and its opposite over here, all right, contain, let's say, 95% of the data in the middle, okay? So in the example of 95%, 1 minus alpha would be 0.95, which means alpha would be 0.05. That would be the two light green areas combined would give you 0.05. And then if you divide that in half, you would get half of that, or 2.5% down here, and the other 2.5% up here. Okay. So in general, that 2.5% is called alpha over 2. The value of Z that cuts off the top alpha over 2 proportion of the distribution. That's called a critical value. Notice it says the way that we find those is either using technology or using table A2 that we were using in chapter 6. Okay, so the first example of finding a critical value, find the critical value Z sub alpha over 2 corresponding to a 95% confidence level. It's likely that we've done this problem before. It just wasn't worded like this. So let's see. A 95% confidence level corresponds to alpha equals 0.05, which means alpha over 2 is 0.025. The figure on the next slide shows that the area in each of the green, let's look at that real quick. Okay, so we're looking for Z sub alpha over 2 for a 95% confidence interval, which means 95% in the middle. So I start with 95%, which means alpha is 0.05 of the confidence level. Divide that in half, you get 0.025. So that 0.025 sits up here. And if I subtract that from 1, that gives me 0.975, which is all the area to the left of this mystery z-score. You do see the mystery z-score there. Just pretend you don't for a second. So if you look up this value 0.9750 in the table, let's skip over to the table here. Oops. That's going to be on the next page. And let's see, 0.9750, there it is. Okay. So I read over here, I see 1.9. I read up here, I see 0.06, which means that that z-score cutting off the top 2.5% is 1.96. Notice at the bottom of your table, it gives you common critical values for the three most common confidence levels that we're going to be using. So we just found the one for 0.95. It's 1.96. If your confidence level is 0.9, then your critical value is 1.645. And if it's 0.99, then your critical value is 2.575. So in the future, when we are dealing with one of these confidence levels, we will likely just say, okay, now remember that the critical value for, say, 0.99 is 2.575, okay? So as long as you have a copy of this table handy, you can find this reference on the bottom of the positive z-score side of table A2. All right. So this is 1.96, which means that its opposite is negative 1.96. In most of the formulas that we're going to be using, we're just going to use the positive one. Okay, and so again, here is the table that I was just showing you on table A2, the critical values associated with the most common confidence levels. All right, that brings us to margin of error. When data from a simple random sample are used to estimate a population proportion P, the difference between the sample proportion, P hat, and the population proportion is called an error. So it's not an error as in a mistake, it's just an error as in it differs by this much. The maximum likely amount of that error is called the margin of error. And the notation that we use for margin of error is a capital letter E. There is a probability 1 minus alpha, for example, 0.95, that the difference between P hat and P is E, that margin of error, or less. So the margin of error is also called the maximum error of the estimate and can be found by multiplying the critical value and the estimated standard deviation of sample proportions. So we're going to put that all in a nice formula here. Well, starting right now. So here is the formula for the margin of error. Your margin of error is going to be your critical value which comes from your confidence level, times the estimated standard deviation of sample proportions. And that estimated standard deviation is the square root of p hat times q hat. Q hat would just be 1 minus p hat divided by n, the square root of all of that. Okay, notice that the divide by n is also under the square root. So we'll have to be careful when we put that in the calculator. All right, so our objective going forward is to construct a confidence interval used to estimate a population proportion P. So just reviewing the notation, P is the population proportion, P hat is the sample proportion, N is the number of sample values, the size of the sample, E is the margin of error, and Z sub alpha over 2 is the critical value, which again is the Z-score that separates an area alpha over 2 in the right tail of the standard normal distribution. Okay, requirements for constructing a confidence interval. The sample has to be a simple random sample. The conditions distribution are satisfied. You have a fixed number of trials. The trials are independent. There are two categories of outcomes called success and failure, and the probabilities remain constant for each trial. There are at least 5 successes and at least 5 failures. This is just another way of saying what we said in the normal approximation to the binomial section. So at least 5 successes. There are at least 5 successes is just another way of saying n times p is at least 5. And at least 5 failures is just another way of saying that n times q has to be at least 5. All right. Next. Here is the formula for the confidence interval. So once you calculate that margin of error that we talked about earlier, you basically plus or minus that onto the sample proportion, okay? So there are several different ways to write confidence intervals. One way is like this. P hat minus E and P hat plus E will be specific numbers once we do all of our number crunching. So for example, 0.405 might be the number that's here, 0.455 might be the number that's here, okay? I usually prefer to write my confidence intervals either like this or like this. Okay, so you'll see that when we get to our first big example, which is coming up here shortly. And your book always has very specific rounding advice. And they suggest that when you're doing a confidence interval for estimating a population proportion, that you round your interval limits to 3 significant digits. Okay, so now we're ready to start constructing our confidence intervals. So the steps for that are first to verify that the requirements are satisfied. Next, use technology or table A2 to find the critical value that corresponds to the desired confidence level. And then we're going to evaluate our margin of error using the formula that we were looking at a few slides ago. Using the value of that margin of error and the value of the sample proportion p hat, we'll find the values of the confidence interval limits, which are p hat plus or minus E, and then round those confidence interval limits to 3 significant digits. Okay, so here is our example. We noted that a Gallup poll of 1,487 adults showed that 43% of the respondents have Facebook pages, which means that N is 1,487 and P hat is 0.43. So first we're going to find the margin of error E that corresponds to a 95% confidence level. Then we'll find the 90% confidence interval estimate of the population proportion P. And then based on these results, we can answer the question, can we safely conclude that fewer than 50% of adults have Facebook pages? Okay, so first the requirement check. The polling methods used by the Gallup organization result in samples that can be considered to be simple random samples. The conditions for a binomial experiment are satisfied because there is a fixed number of trials. The trials are independent. There are two categories of outcome, success and failure. Either the person has a Facebook page or they don't. And that probability remains constant because the probability of having a Facebook page is fixed for a given point in time. And then with 43% of the respondents having Facebook pages, the number who have Facebook pages would be about 639, which means the other 848 do not. So the number of successes and the number of failures are both at least 5. So all the requirements are met. Okay, the confidence interval and margin of error can be easily found using technology. So we can look at what the stat disk display looks like on the next slide, but we'll also do it the regular way. Okay, so that display looks like this. You put in your confidence level, put in your sample size, number of successes, and they give you the confidence interval. Okay, so this is the way I normally do it. First of all, 95% confidence level. That was the example we did earlier. The critical value associated with that is 1.96. P hat is 0.43. That's our sample proportion, which means Q hat is 1 minus 0.43, which is 0.57. And N is 1,487. So when you plug those numbers into the margin of error formula, Z sub alpha over 2 is 1.96, P hat is 0.43, Q hat is 0.57, N is 1,487. So what you should do right now is put this expression into your calculator and make sure that you get the same answer that they did, 0.0251636. All right, so now we'll construct that confidence interval. We knew P hat was 0.43. We just figured out E is 0.0251636. So when you substitute those values and round to 3 significant digits, you get that the lower confidence level is 0.405, the upper confidence level is 0.455. So that is our 95% confidence level. Based on that confidence interval, it does appear that fewer than 50% of adults have a Facebook page, because remember, we are 95% confident that this interval contains the true population proportion. 0.5 is not within that interval. So it does seem pretty likely that fewer than 50% of adults have Facebook pages. Okay, and then they also had this question attached to letter C, write a statement that summarizes the results. So this is what they came up with. 43% of adults have Facebook pages. That percentage is based on a Gallup poll of 1,487 randomly selected adults in the United States. In theory, in 95% of such polls, the percentage should differ by no more than 2.5 percentage points in either direction. In reality, I see statements like this all the time, again, attached to polls. Usually they don't say all this. Usually they just say, you know, they may say something like that percentage is based on a Gallup poll of 1,487 randomly selected adults in the United States and has a margin of error of 2.5%. All right, let's see, analyzing polls. Analyzing polls voluntary sample or a convenience sample, something like that. The confidence level should be provided. The sample size should be provided. And except in relatively rare cases, the quality of the poll results depends on the sampling method and the size of the sample. The size of the population is usually not a factor. Okay. So if you selected 1,000 random adults in Merced, the margin of error and everything else should be the same as selecting 1,000 random adults in a smaller town like Delhi. Okay, never think that poll results are unreliable. The population size. Again, it really goes by the sample size and not by the population size. All right, now we're going to go the other way. Suppose you're given the confidence interval and you have the lower and upper limits. Can you get P hat and E out of that? It turns out you can. It's very easy. First of all, if you picture that 0.405 to 0.455 from the last example, those are the upper and lower limits. P hat should be right in the middle. So what they're telling you here is to find P hat given the confidence interval, just take the mean of the upper and lower limits, add them together and divide by 2. So that seems pretty logical. The margin of error, you take the width of the interval, the range between the upper and lower limits, and divide that by 2. Okay. The margin of error is the distance from P hat to one of the limits of the interval. Okay, so for an example of that, the article high dose nicotine patch therapy includes this statement: of the 71 subjects, 70% were abstinent from smoking at 8 weeks. And this is based on a 95% confidence interval, 58% to 81%. And they want us to use that statement to find the point estimate P hat and the margin of error E. So using those formulas that we were just looking at, here is your lower limit, here is your upper limit. So if you average those together, that will give you P hat. The mean of 0.81 and 0.58 is 0.695. So that's where they got the 70 in the statement of the example. And then the margin of error, you just take the upper limit minus the lower limit and divide by 2. And that comes out to 0.115. So I added a statement here that kind of explained what that means. If you were given the confidence interval 0.58 to 0.81, you could rewrite it as 0.695 plus or minus 0.115. So the advantage is that it makes the point estimate and the margin of error very easy to see. All right. And now that brings us to finding the sample size required to estimate a population proportion with a given margin of error. So remember at the beginning, I said, suppose you wanted your poll results to be accurate to within 2%. Here's how you do that. First, you need notation again. P is the population proportion. P hat is the sample proportion. N is the size of the sample. E is the margin of error. And Z sub alpha over 2 is the critical value associated with your given confidence level. Okay, so there are two situations depending on whether or not you know the sample proportion. If you know the sample proportion, then what you do is your required sample size will be the critical value squared times P hat times Q hat, and then divide by E squared. E is the margin of error. Okay, that's if you know P hat. Now, if you don't know P hat, which kind of makes sense because remember the goal here is to find the minimum sample size needed to get a certain margin of error. it makes sense that I wouldn't know what the sample proportion is because I don't even know what my sample size is yet. So maybe I haven't come up with the sample proportion yet because I haven't even collected a sample. Okay. So if that's the situation you're in, then you do n equals the critical value squared times 0.25 divided by e squared. So this is kind of a fun algebra problem, actually. The reason for the 0.25 is because that is actually the maximum possible value of p hat times q hat. Okay. The worst case scenario is that p hat is 0.5, which would also make q hat 0.5, and that's how you would get the 0.25. If p hat is anything other than 0.5, then p hat times q hat is going to be smaller than this. So this is an absolute worst case scenario right here. Okay, and then this is pretty important. So if your computed sample size n is not a whole number, which usually it won't be, you want to round that value up. Okay, so just imagine that n came out to 602, or take their example, 1067.11. That's saying that you need a sample, and let's say you're doing a poll. It's saying you need a sample of at least 1067.11 adults. Well, you can't have 0.11 of an adult, okay? So the only way to have at least 1067.11 adults is to have 1068. Because if you round it down to 1067 the way you normally would, that's not at least 1067.11. Okay. So always, always, always round sample sizes up. Okay, so here's an example of finding minimum sample size. When the author of your textbook, was conducting research for this chapter, he could find no information about the percentage of adults who make online purchases. Yet that information is extremely important to online stores as well as brick and mortar stores. If the author were to conduct his own survey, how many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? So first, we're going to assume that a recent poll showed that 80% of adults make online purchases. And then we're going to assume that we have no prior information suggesting a possible value of the population proportion. Okay, so first, letter A, with a 95% confidence level, our critical value is 1.96, as we figured out before. The margin of error is given to be 0.03. The prior survey suggests that P equals 0.8, which means Q hat is 0.2. And since we have an estimated value of P hat, we're going to use this formula. 1.96 goes in for Z, 0.8 goes in for P hat, 0.2 goes in for Q hat, and then 0.03 goes in for E. That comes out to 682.951, and we're going to round that up to 683. So in order to estimate the proportion of adults who do online shopping, we need a sample of at least 683 adults. Now, if we didn't know P, then we have to use the other version of the formula, which is this one. So you put 1.96 in for Z. Instead of P hat, Q hat, you just put 0.25. Put 0.03 in for E. That comes out to 1067.11. And again, you have to round that up to 1068. So knowing we're not having a value for P hat is, instead of a sample of 683 adults, you now need a sample of 1068 adults. So it is helpful to have a working value for P hat if just to collect a preliminary sample and use that to get an estimate for p hat. All right, so to be 95% confident that our sample percentage is within 3 percentage points of the true percentage for all adults, we should obtain a simple random sample of 1,068 adults. That's if we have no prior knowledge of what p is or p hat is. Okay. So this is what we said on the last slide. A larger sample is required if you have no prior knowledge of p hat. And that's the end of section 7.1.